Welcome to myprojectbazaar.com. Now we are discuss about our project. Our project title is Approximate DCT image compression using inexact computing. Now we are going to discuss about the abstract of our project. Our project abstract is given the privileges of joint photographic exporting a group, JPEG composed images, optimization image reconstruction from the compressed format remaining on important problems. Instead of a simply reconstruction, a pixel block from the center of the index, discrete cosine transform, DCT coefficient, quantization bins, and soft decoding reconstruction of a block by selecting the appropriate coefficient values within the index bins with the help of signal periods. The challenges thus lies in how to define the suitable periods and apply them effectively. In this process, we comparing the three image periods: Laplacian periods for DCT coefficient, sparsity periods, and graphical signal smoothness period for an image patches, to constructing an efficient JPG support decoding algorithm. Especially, we first using the Laplacian period to computing the minimum mean square error initial solution for each code block. Next, we show that while the sparsity period can reducing the block artifact, limiting the size of the over completed dictionary, would lead to poor recovery of high DCT frequencies. To alleviate this problem, we defining a new graph signal smoothness periods based on the left eigenvector of the random walk graph Laplacian matrix compared with the previous graph signal smoothness periods LERAG, distributable images filtering properties with low computational overhead. We decomposition how the factoriate recovery of the DCT frequency of a piecewise smooth signal via an interpretation of low graph frequency computation on relaxed solutions to normalized cutting the spectral clustering. Finally, we constructing the soft decoding algorithm use the three signals period with the appropriate period weights. Experimental research shows that our proposed outperforms the state-of-art soft decoding algorithm in both the objective and subjective evaluating the noticeably. Now we are going to discuss about flow of our project. First one is an image acquisition. The first stage of any vision system is the image acquisition stage. The image acquisition is the digitalization and storage of an image. After the image has been obtained, the various methods of reprocessing can be applied to the images to performing the many different vision tasks requiring today. The first, capturing the input image from the source file by using a getFile and IMRead function. Next one is an get a block size, and if I get a block size is 8 or 16 means it will go to the DCT. DCT, first the exception, the intensity of the variances of 8x8 non-overlapping block in a JPG images is derived. The expectation is determined by the Laplacian performing of discrete cosine transform, coefficient distribution of the original image, and quantization step size is used to JPG compression. The second, some interesting properties that describing the behavior of the various local variations under the different degrees of JPG compression image discussed. Finally, both the simulation and the experimental are performed to verify our derivations and discussion. The theoretical analysis present in this process providing some new insight into a behavior or local variance under the JPG compression. Next one is a quantization. In this quantization, the algorithm uses the specified final images quality to level to determine the constant values that are used to deriving the frequencies. A constant of one significant number losses. On the other hand, the constant of 255 in the maximum amount of losses for a coefficient. The constraints are calculated according to the users, which is hierarchical values are known. Next one is a dequantization. The decompressor is an JPG image is basically the sample as the performing the compression steps in the reverse, and it's in the opposite order. It's beginning by retrieving the Hoffman table from the images, decompression of the Hoffman coding in the images. Next, it's decompressing the DCT values for each block, since they will be first things needed to decompressing a block. Next one is an inverse DCT. The phases of two discrete cosine transform of the images were be converted into a data from the spatial domain to the frequency domain. Thus, we must to obtain the opposite here. We converting the frequency values back to the spatial value. This is easy to accomplishing by inverse discrete cosine transform. The IDCT takes each values in the spatial domain and examine the computational that each of the 64 frequency values make it to the pixels. It mainly causes decompression of a JPG images must be done more than the compression of the original image. Next one is a performance measures. In the performance analysis, this is done calculating the PSNR and the MSE value. PSNR means peak signal to noise ratio, is approximated to human perception of the reconstruction of the quality. It is calculated based on the mean square error rate, that is MSE. PSNR value is high for an enhancement process. Now we are going to discuss about output of our project. First, open the MATLAB or 2013 version, then go to the current folder, select main.m file, right click the main file, click run button. Now we are going to select the dataset. Now I selected a 4.jpg image. Now here now we are given the input for block size 8x8 or a 16x6. Now I give the 8x8 matrix. So this is input image. In the pre-processing stage, I am converting the channel RGB 3 channels. So first channel DCT images is displayed here. Next one is a quantization image. Next one is a dequantization image. This is the decompression values. Next one is an inverse DCT. Finally, we are calculating the deconstruction image. In the performance measures, we are calculating the MSE and the compression ratio for this project. Thank you for listening. Our demo is completed. Thank you.